Hello. Hey. I'm not sure if somebody was supposed to introduce me or anything, but now is the time to begin, so I guess we'll begin. Okay. I'm Mike. Sorry for my Russian. My Russian is so bad that it's English. I am a software developer at a company called Consensus. We're in New York City. So, you all are going to be hacking this weekend and trying to write some smart contracts, which are applications that run on blockchains in a decentralized manner. So these are applications that do not require servers, which is kind of an interesting idea. So I usually give like a 1 hour talk on like the basics of how blockchains work, but we don't have much time. So I'm going to try to give you like a 20-minute talk on how blockchains work, and then spend another 20 minutes talking about how you can actually write smart contracts. So I'll talk about programming smart contracts, and then Astrid will talk after me about how you can deploy your smart contracts. Yeah, okay, so we can begin. So I'll try to move through this relatively quickly since we don't have that much time. Okay, so blockchains for hackers. What do you need to know? One thing that you need to know, I was given this slide. I assume it says what I was told it says, which is that if you go to this URL here, you can get some free Azure credits for using throughout the hackathon. There's also going to be a group chat for this hackathon, so if you go to this URL, you can log into the group chat. It should be very helpful. You'll be able to ask each other questions, help each other out. You know, try to be friendly at a hackathon. Hackathons are all about making friends and having a good time, in my opinion, but that's just me. Also, if you're very competitive and you do manage to win, there's an Xbox, so that's kind of cool. Okay, so how do blockchains work? I'm only going to cover what is like strictly necessary right now for writing smart contracts. So we're going to skip over like the actual consensus formation part of things and just talk about like what data is available to you as a programmer when you're writing these applications. What data do you need to provide? How do you need to be thinking differently than if you're just writing like Java or something? So our prerequisites for understanding blockchains, before we like know what a blockchain is, there are 3 things we have to understand first. Hashing functions, public key cryptography, and digital signatures. So hashing functions, these are least important for you right now. Basically, they're fingerprints for data. So you take some data of arbitrary size, you run it through a hashing function, you get some fixed size data out. This output is unique, or there's like, you know, the odds that 2 inputs produce the same output are just astronomically small. And what's important about these is that the outputs leak no information about the inputs. So for example, we have 4 hashes here. These are SHA-256 hashes, which is the hashing function used in Bitcoin. So the first one, you could try to take a guess at what input produces that output. It's my name. The second hash there, so an important property of hashing functions is if you change anything about the input, if you flip even 1 bit of input, every bit of output will flip with a 50% probability. So if I just change the first letter to uppercase, you get a totally different hash. If you take that second digest and use it as an input to a hashing function, you get the third digest. And then finally, totally unrelated, if you take the Gettysburg Address, which is a famous speech in American history, you get that final hash output. So what's important to see here is that like if all you knew were these outputs, there would be no way for you to guess the inputs. And also, like these 2 hashes, which are based on similar inputs, have no more of a relationship to one another than, you know, this hash and this hash, which have 0 relationship with one another. So hashes, you can use them as like content fingerprints. Hash functions can have multiple inputs, so 1 input, 2 input, 3 inputs, 3 different digests. So what are hash functions useful for? Like I said, they're like content fingerprints. So you have, you know, some file of arbitrary size. The hash you get of that file is going to be unique, so it's like a fingerprint of the file. You can use this to prove that some data exists without actually revealing that data until later. And importantly, for understanding blockchains, they're useful for playing guessing games, but we'll talk about that in a bit. Okay, second thing that you need to understand for like understanding blockchains at a basic level is public key cryptography. So our problem here, Alice wants to send a message to Bob, but the NSA is watching the network. So Alice says, "Hello, my friend. Bob receives this message, but so does the NSA, and now the NSA knows that they're friends, and we don't want that. Maybe they want their friendship to be a secret. All right, so we solved this with public key cryptography. So public key cryptography is all about public-private key pairs. The public key is derived from the private key. The public key leaks no information about the private key, so I can share my public key with all of you, and none of you will be able to know what my private key is on that basis. So what this is useful for, what we use this for, information which is encrypted with one of these keys can be decrypted with the other, and that goes in either direction. You can use either the public or the private key as the encryption key, and then the opposite key is used as the decryption key. So in practice, to use this to send secret messages, Alice and Bob, they have their private keys on their computers. The public keys live on the network, so the NSA, they can see what these public keys are. That's fine, doesn't bother us. What Alice is going to do to send her secret message, she's going to input her message along with Bob's public key into the encryption function, and what she gets out is some ciphertext, right? So she provides her plain text, the message, and Bob's public key, and gets ciphertext out, right? So we're going to send that over the wire. The NSA sees the ciphertext, but it doesn't mean anything to them. So Bob receives the ciphertext. He has a decryption function. He inputs the ciphertext and his private key to get the original message back out. So we encrypted the message with Bob's public key, which everybody knows. We sent it to Bob, and because only Bob knows the private key, only Bob can actually decrypt the message. So that's how we can use public and private keys to send secret information over a compromised network. Okay, final thing that you need to understand to have like the prerequisites down for wrapping your heads around blockchains are digital signatures. So how can we send secret messages over a wire and know that an adversary is not manipulating those messages? So here, Alice is saying to Bob, hello, my friend. The NSA intercepts that message, and they change it to, you are my worst enemy, which is like so bad for their friendship. I mean, you can imagine the NSA might want to do this between like governments that communicate with one another. So this is a problem that has to be solved. How is this solved in real life? So we use digital signatures to solve this problem. What we want to do is prove that a message which we received is exactly the message which was sent. Furthermore, we want to prove that the message we receive was sent by the person who we expect it to have been sent from. So it's not enough to know that a message which may have been sent by the NSA is exactly that which they sent. We want to know if it was sent by the NSA, that it wasn't actually sent by our friend. Okay, so we're going to combine hashing functions and public-private key cryptography to produce digital signatures. So here we're on Alice's computer. P is our plain text. This is our message that we're going to send, and we're going to encrypt it just like before using Bob's public key. So we get our ciphertext out, right? And then down here, to produce the signature for this message, we take the plain text. So we had our plain text here, we have plain text here. We're going to hash that plain text, so we get a digest, we get a fingerprint of the plain text, right? Then we're going to encrypt the digest using Alice's private key, okay? So we encrypt the message using Bob's public key. We encrypt the signature using Alice's private key, right? So we get a ciphertext and we get a signature. Probably doesn't make sense yet how this is helpful, but when we get to Bob's side of the equation, you'll see how he can use this to prove that the message he receives is legitimate. So we send the ciphertext and the signature over the wire. Bob receives this. This is the most complicated graph. They don't get any more complicated than this. After this, it's all relatively easy. Okay, so we're on Bob's computer now. How is Bob going to prove that the message he received hasn't been manipulated by the NSA or some adversary? So he receives the ciphertext, and he uses his private key to decrypt that, just like he did before. We've seen this already, so he gets the plain text out. Now he wants to prove that this plain text hasn't been manipulated. So he takes the signature. Now remember, the signature was encrypted using Alice's private key. Okay? Bob doesn't have Alice's private key. Only Alice has Alice's private key. But Bob does have Alice's public key. So he can use Alice's public key to decrypt the signature and get the digest, the hash of P out, right? So now he has the plain text and what is presumably, what is hopefully a fingerprint of the plain text. Bob can hash this plain text that he has to produce his own digest and see if these two things match. If they match, the message was not manipulated. If they don't match, somebody is trying to do something funny. So just to like prove to yourself that this actually works, we can look at how you might try to attack this system and why it wouldn't work. So let's say the NSA sees this message. Alice is sending a heart. The NSA wants to change it to a frowny face, right? So Bob is going to receive that. When Bob decrypts the signature on this message, when he decrypts the signature, that will be a hash of a heart. It will not be a hash of a frowny face. So those things aren't going to match, right? So Bob's going to know, okay, this message was manipulated. If the NSA tries to attach their own signature to the message, so the NSA, they can alter this message and then just sign it themselves, the problem is they don't have Alice's private key. So Bob is expecting to receive this message from Alice. So when he tries to decrypt that signature using Alice's public key, it'll fail because it was signed with the NSA's private key. Okay, so normally I would take questions, but we don't have much time, so I'm going to keep going. Basically, what we get out of all of this is we can prove that a message which we receive was sent by the person we think it was sent from, and that it wasn't altered in any way before it got to us. Okay, so now we're ready to learn about blockchains, or at least like the basic parts that we need to understand for the purposes of like winning this hackathon. Okay, so what are blocks? They're called blockchains. What are the blocks? Blocks are answers to a guessing game. So normally I'd go into a lot of details about why we play this guessing game in blockchains. Basically, we have to play a guessing game. The core innovation of Bitcoin is that Satoshi Nakamoto figured out how to replace a central validator, a trusted central validator, with a guessing game, which is like kind of crazy. If you read the Bitcoin white paper, it's very interesting. But what you need to know right now is that the inputs to this guessing game, the answers that we provide to the guessing game, consist of three things: a list of transactions, the previous answer, or rather a hash of the previous answer, and this thing called a nonce. A nonce is a number used once. It's just a random number, right? So basically, we are providing these three inputs to a hashing function, and we're trying to get out a hash that has a certain number of leading zeros. So the network is going to agree that the guessing game we're playing has a certain difficulty. That difficulty is defined by how many leading zeros are required in the output of this hashing function. So this would not be a winning answer because it has 0 leading zeros, has no leading zeros, right? So there are transactions that get broadcast on the network, right? And those are what they are. We can't really change those if we're playing the guessing game. We just have to kind of accept them and use them. Similarly, the previous answer, we can't change what the previous answer was. It happened in the past. We just have to use that. So our nonce is what we make guesses on the basis of. That's just a random number. We can use whatever we want there. The important thing to know here, like the key takeaway, is that transactions on the network become part of the network's history every time a block is produced. Every time somebody finds a winning answer, transactions included in that answer are part of the network's history permanently. Because the next block, the next answer that someone produces, will have to reference the previous block's hash. And that previous block has the transaction list in it, right? So when a transaction gets mined, it's being included in the blockchain's history in a permanent way. That's the takeaway. All right, so what are transactions? So I'm going to skip over like what transactions actually are in Bitcoin because it's kind of complicated. For now, we can basically say a transaction kind of looks like that. Alice sends 5 to Bob. Like, that's really not how it works. It's more complicated. But abstractly, it's okay to think of it that way. Now, the way that Alice proves that she actually has 5 Bitcoin to send to Bob is so there's going to be 5 Bitcoin in this data structure called a UTXO, which is an unspent transaction output, right? So that unspent transaction output is going to have a hash of Alice's public key inside of it. And this is going to prove that Alice is the owner of this UTXO, of this 5 Bitcoin. Alice proves it by signing, producing a digital signature of that hash with her private key, which anyone else can then decrypt using her public key and see that the hashes match. Only the person who possesses the private key corresponding to the public key which was hashed should be able to produce this correct signature, right? So don't worry about like wrapping your mind around that too much right now, because again, we're just hackers. We're trying to win this hackathon. This isn't like a computer science theory class. So the important thing to understand here is that UTXOs, Bitcoin, cannot be moved without proving ownership over them using a digital signature, right? Okay, so, and well, I'll mention at the end, we're probably not going to write programs for Bitcoin in this hackathon. If you do, good for you. You'll probably be using a programmable blockchain, so you might be using Ethereum, or at least you'll be using the Ethereum virtual machine, most likely. The principle is the same in Ethereum. You can't make an update to the blockchain, which is a database. The blockchain is basically a database. You can't make a valid update to the blockchain without providing a signature proving that you have the rights to make whatever state change you're trying to make. We'll talk about this more in a minute. Okay, finally, what are these addresses that we've been talking about? So like Alice and Bob, if Alice is sending 5 Bitcoin to Bob, she's sending 5 Bitcoin to Bob's address, right? So what are these addresses? They're public-private key pairs, like we talked about before. The private keys are just random data. The public keys are derived from that random data using, in Bitcoin's case, this elliptic curve digital signature algorithm, ECDSA, and the SECP 256K1 curve, which you do not need to know about as developers, just trivia. But the point of this is, like, the interesting thing about that is, it's just math. There is no Bitcoin company that you have to go through to ask for like an account to use the Bitcoin system. You could theoretically just like do it on paper. It would take you a few hours or a few days, but you could just do it yourself. Certainly you could write software to do it for you, which is what people have done. So that is one of the big things that makes Bitcoin decentralized. To participate in it, you don't need to ask anyone's permission. You just need to generate a public-private key pair, and that's just math. Nobody owns that. All right, so what makes a blockchain a blockchain? We talked about very briefly what the blocks are. They're answers to this guessing game. We didn't even talk about why we play the guessing game. But what makes it, what about the chain? Okay, knowing why it's a blockchain truly doesn't matter for the purposes of the hackathon. The chaining part, it defends against, so we have this database, right? The blockchain's a database, and anybody can write to it. So it's like, oh, well, what stops anybody from like messing up this database? Usually when you have a database, you have a database administrator who makes sure that people don't just, you know, maliciously delete information or anything. So if you're curious about the chaining part, ask me afterwards. But the reason that it is not important for you to understand for the purposes of winning this hackathon, for the purposes of like writing these applications is going to win you the Xbox, is that when you are writing applications for blockchains, the consensus layer of things, like the security layer, is abstracted away from you. You don't care about it. As a programmer, all you need to know, is that you can write changes to this database and know that they can't be overwritten so long as the changes which you made yourself were valid. If you're trying to do bad things or things that you shouldn't be able to do, your changes might not make it into the database. But if you're playing by the rules, all you have to know is that in spite of the fact that there's no like central authority looking out for you, your changes will be made. They will be stored permanently in this database called a blockchain. So, I mean, you know, you can see how like the chaining is because we have to reference the previous block hash, but whatever. Don't worry about it. Okay, so what makes Bitcoin better than like Zucker dollars or an Amazon gift card or a Starbucks rewards card? So like if Mark Zuckerberg and Facebook decided to start printing their own money, and I bought Facebook dollars with US dollars, then Facebook owns my money. So there was this company called eGold back in the 90s that tried to do digital currency, and it was kind of an exciting thing, but eGold went bankrupt, and then everybody who owned eGold suddenly had no eGold. So it would be uncool if like the private company which issues my money goes bankrupt and then I have no more money, or if their database got hacked, or if I broke their terms of service, like I posted some picture of myself drinking too many beers, and they were like, that's too many beers for our terms of service. You have no more money. That would not be cool. So with a system like Bitcoin, with this decentralized system, so like if Facebook goes out of business, you're done. If a single Bitcoin miner goes out of business, doesn't matter. If there's like an earthquake in California, that's fine. Bitcoin is all over the world. Like the network remains online. It's all good. There's no terms of service, nor would there be any means to enforce a terms of service. It's open source, so presumably less buggy. And interestingly, there's no central database of public-private key pairs in Bitcoin. So you hear all the time about banks and retailers which get hacked, and then like 1 million customers' credit cards all get stolen. There is no central honeypot attack vector in Bitcoin. Like the biggest attack vector in Bitcoin is against a single individual. So I could get hacked, or like one person could get hacked, but you know, it would just be me who lost my information, and it would kind of be my fault. There is no like one central database which would be catastrophic for the whole network if it were to be compromised. Okay, so you don't really understand Bitcoin. This slide is a holdover from the normal, much longer version of this talk, but you understand it sufficiently, maybe, for the purposes of building some applications for it. So now we're going to talk about actually writing those applications very quickly. So this is like the theory part of the talk. Now we'll get into like the practical part of the talk. What do smart contracts actually look like? Any questions, by the way? All right, cool. Stop me anytime. Okay, so that was blockchains for hackers, and now we'll do smart contracts for hackers. Okay, so smart contracts. Applications, which we write for blockchains, are called smart contracts. That's kind of a controversial name. Some people prefer the term agent. Some people don't like the word contract. I call them smart contracts, so we will call them smart contracts. All right, so probably the blockchain you're going to be using in this hackathon, if you are using blockchain, is called Ethereum. So in Bitcoin, what we're basically doing, the thing that we're maintaining consensus over, is essentially a spreadsheet. It's not really a spreadsheet, but you can think of it like a spreadsheet. I have 5 Bitcoin, you have 10 Bitcoin, she has 37 Bitcoin. It's like, you can think of it like a spreadsheet, right? And we're making updates to that spreadsheet, and we are collectively maintaining consensus over the state of that spreadsheet at any given time, right? So that's pretty cool. What we do with programmable blockchains to make them, so you can imagine like it's hard to program in Excel. It's hard to write complex programs in spreadsheets. So what we do with programmable blockchains is rather, instead of maintaining consensus over a spreadsheet, we maintain consensus over a virtual computer. So if you've ever written Java, for example, you've used the Java virtual machine. It's like, you know, a virtual computer. It's a virtualization of a CPU. On Ethereum, we use the Ethereum virtual machine, and it's the same principle. It's like similar to the Java virtual machine. It's a virtual machine. It's much simpler than the Java virtual machine, but it is Turing complete. You can write any sort of program for it. The Ethereum virtual machine is not at all specific to Ethereum. It was born for Ethereum, but there's another blockchain or a blockchain-esque project called Hyperledger, which is probably going to use the Ethereum virtual machine as its consensus mechanism or as the thing that it maintains consensus over. There's also a project to bring the Ethereum virtual machine to Bitcoin. That project is called Rootstock. So if you learn, people seem to like the Ethereum virtual machine or the EVM for writing smart contracts for blockchains. So even if you're not an Ethereum believer, the EVM itself seems to be going places. It would probably be worth your time to figure out how to write applications for this thing. And also because, as you're going to see, there's some weird things when you're writing applications for blockchains that you need to think about, which you don't need to think about when you're writing applications for, you know, the Java virtual machine or, you know, for Ubuntu or any other target. Okay, so the most advanced language that we have right now for the EVM, and, you know, remember, this is early days. This stuff is like a year and a half old, really. It's a language called Solidity. It's a pretty low-level language. It's a lot like C. So you probably, I mean, maybe you do like school projects in C. I used to do a lot of school projects in C. You don't write production systems in C unless you're writing operating systems. The reason being it's dangerous. You can get seg faults. It doesn't save you from yourself as a programmer. Like personally, I'm like an idiot. I write bugs into my programs all the time. And Solidity does nothing to save you from yourself in that regard. But it's the most advanced language we have right now. It's the language that you will probably end up using for this hackathon. There's another language called Serpent, which is more Python-esque. You could try Serpent. I haven't used it myself, but maybe give it a shot. Okay. I already talked about this. Oh yeah, and just FYI. Sometimes people ask me, they ask me questions like, okay, so I'm writing my program. What do I do if there is, you know, a fork in the consensus? What do I do if like something happens in the consensus process? How do I account for this in my code? And the answer is you don't. Like the reason that it would be so difficult to write applications for blockchains if you had to be thinking about the underlying consensus process. Like I said earlier, you don't. You get to trust as a developer that legitimate changes you write to the blockchain are going to stay there. And nobody else is going to be able to overwrite them unless they have legitimate access to do that. So you don't have to think about the underlying consensus process exactly. There are things you do have to think about, but not that. Okay, so let's look at the most minimal smart contract that you could write in Solidity, which is not on the screen. Hold on, let me open it up. min.sol. And let me see if I can move this to the other monitor. Hold on. We're going to get there. And show. let's see. Okay, so there's that, and here, now there's this. This is that. Okay, here we go. Let's make this full screen. Great, and we'll make it way, way bigger. Okay, so here on the right, this is the most minimal smart contract that you could write. All it is, it's a constructor function which does nothing. The reason I even bother showing you this is just so you get the idea that smart contracts require constructor functions. So if you've ever written any object-oriented language like Java or like Python, you have to have constructors for your objects before you instantiate them. Solidity smart contracts require constructors as well. So that's like just the point I wanted to drive home with this tiny little example. They need constructors. Now I'll show you a more meaningful example of a smart contract. So let's open up, where are we here? Let's open up address registry. Okay, so this is a real smart contract. It's a simple one, but this is like actually one that is deployed on the mainnet. It's actually one that I work with at Consensus. So we have 30 lines of Solidity code here. What we use this smart contract for on the project that I work on, we do a project called Proof of Physical Address. So what we do with this project is we want to make attestations about the fact that somebody has a physical address where they can receive mail. The idea is, if you've ever been on a website and you have to enter like a CAPTCHA code to prove that you're not a robot, that's a little bit annoying. If we could just prove in a programmatic way that you're able to receive mail, generally robots can't receive mail. So this is a smart contract. It lives on the blockchain. What's cool about smart contracts relative to like an API that gets served from a server, so let's say you build your business and like as part of your business's processes, you need to make sure that a customer is like a real human being and not a robot. So you're gonna like call the proof of physical address server and like ask a question to our API and hopefully we give you an answer. But you have the same problem there that you do with like Facebook money. What if we go out of business? Or what if the power goes out at our data center and our server goes offline? So you can't really trust servers 100% of the time. Sometimes they go offline. With smart contracts, we cannot get rid of this thing if we wanted to. Like, we have no means of destroying this smart contract or making it go offline or censoring it. There are things you could build into your smart contract to give yourself the ability to do that, but we did not build any of that into this smart contract. So we have 30 lines of code here. Let me show you what this 30 lines of code does. It should be pretty comprehensible. So this contract is called address registry. So here's our constructor function. This gets called automatically when the contract is deployed. And all we do here, so we have on line 3 a variable called owner. An owner is an address being a public key, right? So when the contract is deployed, the private key, which signed the transaction that deployed the contract, we are able to access the corresponding public key using this global variable called message.sender. So in the Ethereum virtual machine's runtime, code only runs when it's been invoked by some transaction, right? So you can always rely on having globally available information about the message. So you have information about who the message sender was, how much value was included in the message, and some other stuff as well. What we're going to do here is we're going to say that the owner of this smart contract is message.sender. That's all we do in the constructor, right? Okay. Now, down here, let's say somebody, so the way proof of physical address works, you give us your address. We then specify, we generate a new public-private key pair, and we say send $5 worth of ether, which is like the token that runs on the Ethereum blockchain. We say send $5 worth of ether to this address. So the customer does that. We see that they've done that on the blockchain, and when we see that they've sent us a little bit of ether, we send a postcard to their address. That address has a PIN code on it. They come back to our website. They enter the PIN code and specify the address which they want attested to as being able to receive mail. So once they've done that, we get the address and we give it to this function called verify. Verify takes as an argument, it has one argument called adder. Adder is an address, a public key. First thing we do, we say if message.sender equals owner, so the person who deployed the contract. So my colleague Igor is the person who deployed this contract. If the message sender is the owner, we add the address which we're passing in as an argument to this mapping that we have here. So this is just like a hash table. So the key is going to be the address, and we're going to set the value to true, right? Now, the reason we have this little check here is because we want people to, now this is like open source code. You could copy this if you want and make your own open version of it. But we want people to, pay us to send them these postcards. Furthermore, if this contract was just wide open, people could register themselves as having addresses when maybe they actually don't. We only verify addresses after they've given us a PIN code from a postcard that we've sent them. So if I tried to just send some transaction to this smart contract, to the verify function, my transaction would fail because I am not the owner. Like, I can't sign a transaction from the owner of this smart contract because I don't have that private key. We can also de-verify someone. I don't know why we would need to do that. I don't think we've ever done that. Up here, we have like a utility function to change the owner. So say Igor is worried that maybe his private key was compromised. He might want to change the owner, generate a new public-private key pair and set a new owner. And then the final function we have, so this is a public function. This is not, you don't have to be the owner of the contract to use this one. It's just a read-only function. You're not modifying, you're just reading. So it's called hasPhysicalAddress. You provide an address as the argument, and then we return the value that maps to the key in our isVerified map. So if my address is verified and I call that function, providing my address as the argument, it'll return true. Otherwise, it returns false. This is like a very simple API, or a very simple smart contract that provides a service which will never go offline. Yeah. Any questions about this smart contract? I would say, for the purposes of this hackathon, this is like approximately the level of complexity that you should be targeting. I'm going to show you two more complex smart contracts right now, and I'm going to show you why writing smart contracts is hard. Okay. Any questions about this? Cool. Great. We have about 10 minutes. Okay. So that's a very simple registry contract. So like a registry is a kind of generic sort of contract that people make a lot. This is a more complex, or you could say a more complete registry contract. We don't need to look at all the code exactly. We're going to see that they're being much more formal about all this. It's got 200 lines of code here. They have all sorts of utility functions in here. So when we launched Proof of Physical Address, we did it before this master registry standard had been written. So this master registry standard is something that's been audited very carefully by the best Solidity programmers at Consensus to make sure that it has no bugs. So I was saying earlier that smart contracts live forever. They can't be destroyed unless you've specified originally that you can destroy them. So it can be hard to upgrade smart contracts. It's not just you do a git pull and then you reboot your server. That contract's going to live forever. We can talk if you're curious about design patterns for updating smart contracts, but bear in mind, these things live forever if you're not careful. Now, I'll show you a very complex smart contract which turned out to be a disaster because it had a very sad and unfortunate bug in it. Okay, so here we have a contract called the DAO, DAO.sol. Yeah, okay. So this is almost 1,000 lines of Solidity code. And it also imports some other code that it calls on. So total this is probably 1,500 lines of Solidity code. So what the DAO was, DAO is the Decentralized Autonomous Organization. These people had an idea. We are going to put a venture capital fund on the blockchain. Anybody will be able to send money to it, and then those people become voting members of this venture capital fund's board. So like me, as a regular person, I could send some, relatively small amount of money to this smart contract, and then I get a vote on the smart contracts board. We get to decide what we want to fund in a decentralized way. So people were super excited about this thing called the DAO, and it wound up collecting about $150 million US worth of Ether tokens inside of it. There's $150 million of value locked up inside of this smart contract. So like I said, I write bugs when I code things. My code always has bugs, I promise you. Just a question of how many on any given day. So of course you can already see the way that the story ends. The DAO had a bug in it. Basically the way this bug worked, let's see if I can type it out real quick. vim example.sol. So one interesting thing about smart contracts on Ethereum is that anytime you receive a message, you invoke code. So there's a function called the fallback function, which if you don't specify, it does nothing. But you can specify it to do things. You just put this unnamed function in. That's the fallback function. So if you just send ether to a smart contract and you don't want to invoke code, you might invoke code if that person has specified something for their fallback function to do. So I will show you real quick what the bug was in the DAO. So I'm just going to type for a second. Okay, so this is the bug in the DAO, basically. So this looks pretty innocent. So we have this function called withdraw. So say I sent some money into the DAO because I wanted to participate in it, and then I decide I'm bored. I want to get my money back out of the DAO. So I call this withdraw function. And what the DAO did, this is a simplified version, it got the message sender, and it said it was going to send to them, so it had a mapping of balances, which used the sender's address as the key. So we would plug that in, and let's say I had contributed 50 ether to the DAO. So this would send 50 ether to me, right? This line right here, send 50 ether to me. That ether hits my account, and what the hacker had figured out, they wrote into their account a fallback function, which just recursively called the withdraw function again. Now notice, in the DAO, they didn't update this person's balance until after they had already sent the ether. So this line gets executed, line 3 gets executed, the ether is sent to the recipient, they recursively call withdraw, and they are able to just keep withdrawing ether infinitely until the contract is empty. Line 4 here, the one that resets their balance, actually never gets executed because they use their fallback function in a clever way. So what I was saying to interns at Consensus this summer is that when you are writing smart contracts, every application you write is a financial application, and you have to approach it with that level of paranoia and humility. That's why I say try to target a relatively simple smart contract for this hackathon so that you don't shoot yourself in the foot. Okay, so that's just one example of something bad that you can do to yourself. So with 5 minutes left, let's see what else I wanted to cover. Yeah, so be paranoid, be humble. You're going to have bugs in your code, so be very thoughtful about the code that you write. If you write a little bit of code, you can look at it more carefully and find the bugs in it. Be aware of, so this attack with the fallback function, that's called reentrancy. Your code can be re-entered when you don't necessarily expect it to be whenever you call any external code. There's this thing called call depth attacks, which you don't need to worry about for the hackathon, but just to give you an idea that this is not always safe. The call stack in the Ethereum virtual machine is you have 1,024 calls that you can make before you bust the stack. So if you expect to be able to make a call to an external contract and then have that contract call you back, some hacker may run the call stack up to 1,023 entries, call you, and then your external call will fail because you'll bust the stack. You'll be over 1,024 entries. You don't need to worry about that for the hackathon. Don't even care. Design considerations, so privacy. Blockchains are not good at privacy. This is an unsolved problem in blockchains. Any information that you put on a blockchain is public by default. So you might think, okay, I can encrypt the data and store it on a blockchain. You can, but generally not a good idea because you can't process encrypted data, so it's not very useful. And furthermore, if the key which you use to encrypt that data is ever compromised at any point in the future, then that data is pwned permanently. You can't re-encrypt it because things that live on the blockchain live forever. Yes.
So the idea that the philosophy is that all information should be public. Is that right? I mean, in general.
Yeah. So the question is, should all information on blockchains be public in your applications? If you are able to make that assumption that it's okay for your application for things to be public, yeah, you have no problems. if you need to keep information private, it's not impossible to do, but you get into some rather more complex design patterns, which feel free to ask me questions about. It's one of the most interesting topics.
It goes different ways, you know. I mean, the idea is publicity, but if central bank says, I want a blockchain, but I want private blockchain, so what do you answer? What is your answer?
Yeah, so
Blockchain, but private.
yeah, so what do you do if you need to keep information private on a blockchain? So we actually met with the Central Bank of Russia yesterday and had a very interesting conversation with them about how do we keep transactional information private. And the answer is, it's not impossible, but it gets complicated. Let's talk about it afterwards, and I can give you an in-depth answer about how we can keep information private on blockchains. Also keep in mind efficiency. So when we run code on programmable blockchains, you might imagine, okay, what if I'm like a troll and I just put an infinite loop in my code? Every single miner on the network is just going to be running that infinite loop forever, and then the blockchain is broken. How do we prevent this? The answer is users have to pay a small amount of ether for every computation that they do. They have to pay a decent amount for storage. It's expensive to store things on a blockchain because every miner has to store that information forever, right? We also pay a little bit for computation. So bear in mind that your users are paying a little bit of money for every computation that they do using your application. Only put the parts of your application on a blockchain which are actually which require the decentralization and trust factors that the blockchain provides. Like your front end, is obviously not going to be running on the blockchain. Like put as little as on the blockchain as possible because your users pay for it. And then, the last thing, one thing that's really cool about blockchains, so if you're writing a normal web application, you can't look at a user's IP and then assume that they are always going to come back to you with that same IP address. Like it's hard to give people identities in web applications without actually making them, sign up with like an email address. On blockchains, we actually get identities for free. You can make assumptions that users will come back with the same public-private key pair. So like you generally, it's not required anymore that you have a sign-up process for your users. Like they've already signed up by generating a public-private key pair, and you can identify them in a reliable way using that information. So just something to keep in mind when you're designing your applications. And now, with 1 minute left, some free ideas. Think about how you can design governance systems for blockchains. Like you have identities, so people can like vote, and you know who they are. That they are. Say like you only want people to be able to vote who have physical addresses. You can have some voting contract which checks the proof of physical address contract. Do they have a physical address? And if so, they can vote in this election that we're having. Decentralized token exchanges. So like, say like someone has some Starbucks rewards points and I have some like Xbox Live points and we want to trade them to one another. Right now we just have to they have to give me their gift card. It's like difficult. But if we could tokenize those things in a standard way, we could trade them on like an open exchange on a blockchain, which would be pretty cool. And arbitration oracles, let's talk about that. Some more free ideas. These are more evil ones, like gambling and betting. These are things that you can do on blockchains. So what's hard about playing poker on the internet today is I either have to go to some sketchy site where like I put money in escrow and then they may run away with my money. But if you can specify transparently in a smart contract the way escrow is going to work, and your users can trust that their money is never going to get stolen. You can also design like morally questionable financial instruments. I was working with some Microsoft engineers a few days ago, and we designed this thing called a tontine, which is legal in the United States. And what it is everyone pays money into this thing, and then the last living member gets to collect all the money. That's just like fun. Okay, anyway, I'm all out of time. This was a lot of information, and you probably have a lot of questions. So if you do have questions, I'll be here. But you should stick around right now for Astrid's talk, because she is going to tell you how you can actually deploy these smart contracts. So like I just talked about how to write them. Now you're going to learn how to actually deploy them.